Hello everyone, welcome to my channel. And today we'd like to discuss the lecture of 9. The topic is about detection, segmentation, visualization, and understanding. Okay, let us to have a quick look about the last courses about the transformer. There are two parts in the transformer, encoder and decoder. You can see the left side, it is the encoder, and the different architecture in the right side is the decoder. And the most different part is about the masked multi-head self-attention. And there are 3 ways of the processing sequence. The one is the recurrent network, and this way is cannot parallelized and need to compute the hanging states sequentially one by one. And the second one is the convolution. This model is bad for long sequence. Need to stack many layers to build up the larger receptive fields. And the last one is self-attention architecture. And it's very great for long sequence, and each output depends directly on all input. But the question is very expensive. And for example, the computation is the cost is about n squared 2, and the memory of the sequence is about n. So we'd like to know how the vision transformer model work. It works like this. We split an original image to the different patch, and like this, and plant it, and pose the linear projection to the dimensions vectors, and add the position embedding learning the dimension vector prepositions, and extra same as the natural language process transformer, and then output the vectors. We will give a special extra input classification token in the end, and then we got the linear projection into C domain vector of the prediction class score. This is a simple approach for the different ways. Okay, the first part is about the plant and apply a linear transformer, and then the dimension vector pre-patch are the input vector to the transformer, and use the positional encoder to tell the transformer the 2D position of each patch. And we don't use any masking. Each image patch can look at all the other image patches. And we will and the transformer will give an output vector pre-patch. And for the polling, we will use the average poll to calculate, and then apply a linear layer to predict class scores. And next one is a token transformer. It have a little different with the normal one. It's the first one is the pre-normal transformer. It's a linear normal. The original one is the linear normalization outside the residual connections, but kind of the words, but the model cannot actually learn the identity functions. So we made the solution like this: move the layer normalization before the self-attention and the multi-perceptrons inside the residual connections. Training is more stable. And this part is about RMS normal. We instead the layer normalization with the root mean square normalization, and the sequential as like this. This way will be let training more stable. And the last one is the single multi-perceptual. And this part is the different about the multi-layer perceptron part, and we will use a simple low-cost way to generate the output. Okay, another idea is about the mystery of the expert. This means each token gets routed to a small e of the expert, and those are active. Those are the active expert. All of the biggest large language model today, such as the GPT-4, GPT 4.5, Cloud 3.7, and so on, almost certainly use MOE and have small 1T parameters, but they don't publish detail anymore recently. So summary, few changes that have become common. The first one is pre-normal. Second one is RMS normal, and Sui Jalu, and MOE. Today we'd like to talk about two things. The first thing is about the computer vision task. There are three parts: segmentation, semantic segmentation, object detection, and the instance segmentation. And the second part is about visualization and understanding our models. Okay, let us see the computer vision task. We have the three tasks: the semantic segmentation, object detection, and instance segmentation. Let us recall the image classification, a core task in the computer visions. Firstly, we give an image, it is a cat. And then what we will do? We do the paired trained data for each trained image. Each pixel is labeled with a semantic category. At the test time, classify each pixel of a new image. Impossible to classify without the context. How we do the include all the context? How we do the model like this? We will do the slanting windows. For example, we will put the windows like this and slanting it to one position to another position. The problem is it is very inefficient and not resuming share the future between the overlapping patches. And another intuitive idea is encode the whole image with convolutionals and do the semantic segmentation on the top. So what we do? We do the semantic segmentation idea with the fully convolutional network is like this. We input the image and we use the convolutional to process it, and then we do the score part to calculate what is the different part is. Then we got the final prediction. But the problem is convolution at the original image resolution is very expensive. So what we do? The design network as a batch of the convolutional layers with a downsampling and upsampling inside the networks. So we will downsampling first day and upsampling then. So what is the upsampling? Another word we can say it is the pooling. This is the common way is the nearest neighbor and the bed of the nose. And we also use the max polling. Remember which remember which element was maxed. And max up polling use the position from the polling layers. And how we do the normal 3x3 convolutional strata 1 by strata 1 and pad 1, we do like this. Yes. And strata 2 pad 1 is like this. We can interpret straight convolutional as learnable downsampled. This is another example of the upsampling strata 2 pad 1. It works like this. The difference is the overlap. What we can do, we will do the sum of that. And this is a 1D example about learnable upsampling. Output contains copies of the future width by the input, summing it where overlaps in the output. Okay, this is the whole idea about the fully convolutional network with downsampling and upsampling. This is a very famous architecture we always use. Is the UNet. This UNet is based on the idea of the fully convolutional network with the downsampling and upsampling. It works localized this and upsampling phase is like this, and concatenate with the high resolution features maps from the downsampling phase. So, in summary, we do the semantic segmentation from the original convolutional network into the convolutional network with the downsampling and upsampling. But I have to say it's don't differentiate instance. It only care about the pixels. For example, if there are many cases, we will give the semantic segmentation together. So what we can do for the instance segmentation? If we want to solve this part, we need to solve the part of the object detection firstly. So what we do with object detection? For the single object, we do like this. The fully connected process, we got the class score. For example, in this image, we know the class score about the cat is 0.9. If it is a dog, it is about 0.05. And for the car, the score is 0.01. And we also works on the vectors. This means the box coordinates. We know the coordinates of the box about this object. and then we do the corrected and then we do the corrected label cat. Corrected label cat use the softmax loss, and the both coordinators we use the L2 loss to correct the box. This is the multi-object architecture is like this. But each image needs a different number of the output. For example, the first one needs the 4 numbers, and the second one is 12 numbers, and the last one is many numbers. But it works like this if we check detection on the background. We will say, oh, it is the background, and it's not the dog, it's not the cat. We apply a CNN to many different crops of the image, and the CNN classifies each crop as the object or background. So what's the problem with this approach? Yes, it needs to apply CNN to a huge number of the locations, scales, and aspect ratios, very computational expensive. So what we solve this problem? We use the way about the selective search. We found a bubble image region that likes to contain the objects relatively fast to run. For example, selective the search gives the two thousand region proposal in a few seconds on CPU. Let us have a look about what we do. Okay, this approach we also called it is RCNN. So we got the region of the interest from the proposal method, and we wrapped the image regions, and then we forward each region through the convoluted net, and we classify the regions with the same. We predict the correction to the region. For example, the four numbers, dx, dy, dw, and dh. The problem is it is very slow because we need to do many things, and it's independent for what path says for each image. We have an idea is pass the image through the convol net before the cropping the convol features inside. What do we do? Okay, this part is about faster RCNN. Let us see what we do. We use the backbone network firstly, such as the AlexNet, VAG, VisualNet, and so on. And then we got the region of interest from a proposal method. We cropped the resize features, and we got the object category and the box offset. Okay, how the region proposal network works. We image an anchor box of fix the size of each point in the future map, and each point predict whether the relative anchor contains an object. For example, the binary classification. And in practice, we always use the key different anchor box of the different size scale at each point, and short the key times the 20 times the 15 box by either object needs score. Take the top 300 as our proposal. And within each grid cell, ranging from each of the B-based box to a final box with 5 numbers, dx, dy, dh, w confidence prediction score for each of C classes, including background as a class, looks a lot like the RPN, but category specific. This is the famous method of the UOLO. The full name is You Only Look Once, Real-Time Object Detection. Let us see what it do. We give the grid size is S times S, and we for each box output probability P is means probability that the box contains the objects. The B is the boundary box. The P classes it means the probability of the belong to a class. We works on B equal to and many bounding box with the different object probabilities. Then we got the dog, the bicycle, the car, and object detection with the transformer. We always code it the data. Simple object detection pipeline is directly output a seed of the a set of the box from a transformer. No regression, no uncle of box transformers. Match prediction box to ground truth box with the bell patterns matches. Shrink to regress box coordinators. Let's see the detail of that. The backbone firstly, and the transformer then, decoder, transformer, and the encoder, decoder part, and the prediction heads. Then we got the box of the object detection. Next, what we can do, how we can do for the instance segmentation. We do like this. The object detection faster RNN, we always do is like this. And what we can do for the instance segmentation, we add a small mask network that operators on each IOI and predict a 28 by 28 boundary mask. Let's see the detail of masked RCNN. After the ROI align, we apply classification score C, boundary coordinators, and we do next correlational network, and then we predict a mask for each of C class. This is an example of the masked training target. We can see if we focus on the child, we will get like this. If we focus on the kid, we will get like this. And we can use this way to get a very good results. This is example. It's also very good at do the pause. There are some open source about the frameworks. So there are lots of the computer vision tasks what we can do: classification, segmentation, semantic segmentation, object detection, instance segmentation. Okay, next we will talking about visualization and understanding. What way to interpreting a linear classification using a visual viewpoint? We do like this. First layer, visualize feature, and whatever the different the architecture such as Alex night and residual night, residual the different size of the residual night, we can see it also can capture the pattern of the images. But we don't know which pixel matters, and we computed the gradient of class score with respect to image pixel. Take absolute values and max over the RGB channels. So we got the results like this. And we use the same way to calculate the boat, the fruit, the car, the fish, and what's it? Okay, this is the classification mappings, and what we do in this. Firstly, we calculate the last layer CN features, and then we got the score of it, and then we working on the plotted features, and we sampled it, and we to extract the important part, and then we got the class activation maps is like this. We use the CAM to calculate like this. You can see this example, a building and a human in the gym. The problem is it can only apply to last convolutional layer. So what we can do, we can use the gradient weight class activation mapping. We also call it is Grad-CAM. First step, we picked any layer with activation, and we computed a gradient of class score S with respect to A. Global average pulls the gradient to get the width. Computed activation maps. We use this way to get the results about a dog, a cat, and this is an example. And this is a visualizing VIT features. We can get the results like this. So today we are talking about the two-part computer vision task and visualization and understanding. This is all of today's sharing, and thank you for following my channel, and let us to continue on the deep learning. Thank you.